It's okay? Yes? Yes, I think we first met in Vienna, but of course I knew your books and articles before. Even if coming from PDE analysis, I am not certain I am really able to understand everything. So I will stick to a PDE point of view, but still with many links of what you did, or Benedict or other of your group. And I think also, maybe in what I will show, there's a problem. I think there is much to do yet in stochastic analysis. And also, I will try to go back and forth between biology and mathematics, trying to convince you that there are interesting problems which can come from a dialogue with experimentalists. So all the story begins with this experiment. I contacted Weifeng Zhu, a biologist in Canterbury, for another of his articles. But when he came, he gave a talk about what interested him at that moment. And it was this paper published in 2013 in a biophysical journal. So he was looking at fragmentation, pure fragmentation. At that time, I was rather interested in gross fragmentation equations. And so you see from left to right, it is polymer fragmentations. So what they call amyloids, which are very, very long fibrils of proteins involved either in natural development or also in a series of diseases called amyloid diseases. For instance, Parkinson's, Alzheimer's, many others also. Okay, mad cow disease, prion disease. So from left to right, you see, I hope, bottom, it's a zoom. No, up, it's a zoom of the bottom image. You see that when time goes on, the fibrils become smaller and smaller. And their question was, how can we estimate the characteristics of the fibrils? And it was very important for them because knowing their stability, they could imagine if the big ones are more dangerous than the small ones, how they can reproduce itself, etc. So from these images, the problem consists in estimating both the fragmentation kernel and the fragmentation and the defragmentation rates. I will explain to you what they are just afterwards. Okay. Here it is the same. It's newer data done in a series of different proteins. For instance, here alpha-synuclein, it's for Parkinson's disease. The two others, beta-lac and lysozyme, it's normal proteins which do their job normally. I couldn't know exactly what they do, but still. And it's not very clear, but normally you can see that it's smaller and smaller when time goes on. And the interesting thing is that can we compare the characteristics of these different types of proteins? Okay. So what did we do for a mathematical model from that? And that's the point where, of course, if Weifeng Zhu had met one of you, he would have written a stochastic model, but I wrote a PDE. So at given times, Ti, we measure sizes of proteins, one-dimensional sizes. It's the length, x1 of Ti, etc., xn of Ti at Ti, okay? Only stochastic point here, it is that we assume, and of course it's false, I know it's false, but I let you prove that it's false, but almost true, sufficiently true to be considered here. We assume that it's an IID sample distributed along a probability f of t dx, which is given as a normalization of u of t dx. And what is u of t dx? It is the concentration of particles at time t of size x. You see, of course, here, the concentration of particles is not constant. You have a few long particles at the beginning and many small ones at the end. What is conserved is the mass of particles, but not the number of particles. This is why we have a dimensionless here, okay? And what is the equation solved by this concentration of particles? Here it is. So, of course, you can see it as the expectation of a stochastic process. So u of tx, you have the evolution, time evolution, du over dt. And what happens is only fragmentation. So here you have a case, the particles of size x which divide. So it's a minus b of x u of tx, b of x division rate. And I write it here in the specific form of a self-similar fragmentation, because I will stick all the talk to self-similar, so it's better to have only one notation. So you have a k0 of dz, and particles which are larger than the particles of size x divide. So you have this b of x over z, u of t x over z, k0 of dz over z. Okay, so division and appearance of particles of size x. And we have the inverse problem perspective, which consists in saying, okay, I have measurements through this model of u of tx. How can I estimate the division rate b and the fragmentation kernel k0? Okay, and it is exactly the question Weifeng Zhu was trying to answer in his biophysical papers. So just now a few words about the gross fragmentation equation, since the pure fragmentation equation could be seen as a particular case of the gross fragmentation equation. I added here a gross d over dx of tau x power nu, okay, gross rate tau x power nu, and it's the same equation for the rest, okay? And a very important assumption on the kernel k0, of course, it is that it conserves mass. So as I told you, the number of particles is not conserved, but this mass is conserved, so that if you have no growth here, tau equal to 0, with this assumption on the kernel k0, integral of z k0 of dz equal to 1, then you have a conservation of the first moment of the equation, integral of x u of t dx equal to a constant, okay? Important examples, it's not necessarily here that fragmentation is binary, but if it is binary, it means that the integral of k0 of dz is equal to 2. You produce 2 particles at each division. And 2 important cases are the uniform fragmentation case, k0 equal to 2, a Heaviside function of 0, 1, of course, or the so-called diagonal kernel, k0 equal to Dirac in 1/2, or it is also called the mitosis kernel due to equal mitosis for cell division. It is the case when you divide into 2 equally sized daughters. Okay, this is for the model. And now, as mathematicians, we have written the model. And the first thing we thought was, well, what about using what we know? And what we know is, of course, the long time asymptotics. For the long time asymptotics, there is really a huge literature. And of course, Jean works first. So here I write it's first the case gamma strictly positive. So I have now, yes, I haven't said that. I now stick to the case where b of x is equal to x power gamma, okay? Why x power gamma? Well, fragmentation, everything goes to 0. So of course you could, for instance, for cell division, it's interesting to have more complex cases for division rates. But here you're only interested in reality in what happens around 0. So assuming a power law is fully reasonable. And so for x power gamma, we have typically 3 cases. Gamma strictly positive is, I would say, the best case in the sense that you have a nice self-similar behavior, meaning that when t tends to infinity, you have, for instance, one possible result. I didn't write the assumptions on the kernel k0, by the way. You need some assumptions on the kernel. I write them 2 slides later. To have this result, which is not always true. For instance, it is false for the diagonal kernel. But with reasonable assumptions on k0, you have that u of tx behaves approximately like t power 2 over gamma, a steady profile G, the self-similar profile, taken at the point t power 1 over gamma y, okay? And so the idea coming from us mathematicians is to use this behavior to try to estimate gamma, alpha, etc. Alpha, yes. If gamma is negative, it has been studied with probabilistic methods by Benedict Haas. And I don't think there are many works apart from this. Maybe Jean and Alex Watson, but it was not gamma negative. Huh? And then, because when gamma is negative, it means that very small particles break down extremely fast, so that you have shattering, which is instantaneous creation of zero-size particles. Okay. And the case, oh no, it was gamma equal to 0, but with growth with Alexander Watson. Gamma equals 0, it's a critical case for which we have also many interesting things. But biologically speaking, it's not the most interesting ones, at least for my applications, okay? So here, just two examples of a kind. So here you have the uniform kernel, and you see what is happening. So at various times, t equal 1, it's of course, the most spread distribution. T equal 2, t equal 4, you see it's going to 0. And here it is the delta Dirac in 1/2. And you see you go to 0. You should also have oscillations, but I don't write it here. Okay, so okay, we had this model, we had these asymptotic results, and we said our biologists, let's try to use it to estimate alpha, gamma, and K0. Is it possible? First question. Okay. We are not the first ones who are looking at this question. There is a huge literature. We discovered it later, as often when we work, but coming back from the 1960s, it's in the biophysical literature, so it's not very easy to understand what they are doing. But typically, they had the same ideas, using moments, using the asymptotic behavior to try to estimate the fragmentation kernel. Okay, and also this idea comes from our previous works for gross fragmentation equations, for which it is really more natural, because if you have growth, you have a Malthusian behavior, which means that you tend to an exponential growth and a steady profile in size. Here, for pure fragmentation, it's different. You have a convergence to a self-similar profile, okay? What time is it? Yes. I didn't write the, okay. I should write, okay. So the idea is asymptotically, if you have this x power gamma for the fragmentation rate, there is a very nice tool, which is the Mellin transform, which is well adapted to the equation. It is nothing else but the Fourier transform in a multiplicative sense, which is, I define Mellin transform of f as the integral from 0 to infinity of x power s minus 1 f of x dx. And then I have an isometry between L2 of x q dx and L2 of q plus 1 over 2 plus IR. So it's really exactly like a Fourier transform, okay? You just do a change of variables and you have all the theorems for Fourier which apply for Mellin. But it's well adapted here. Why? Because when you look at this term in the fragmentation equation, so first of all, yes, sorry. First of all, remember, so this result, you have this self-similar profile G. When you replace in your fragmentation equation u by t power 2 over gamma g, g of t power 1 over gamma y, you find the equation satisfied by g. What is this equation? It is written here. It is a type of growth fragmentation equation. Okay, this is why it's really linked. And you see that here you have the term for the fragmentation kernel. It's exactly a kind of multiplicative convolution for the Mellin transform. So that when you apply the Mellin transform to the equation, it is written here, you transform this convolution, multiplicative convolution, into a product of the Mellin transforms. Mellin transform of K0 times Mellin transform of G taken in S plus gamma, the plus gamma being linked to the power gamma for the fragmentation rate, okay? And here on the left-hand side, you also have S plus gamma for the division rate here, y power gamma, it gives here. And the derivative, it's exactly as for Fourier, deriving here G gives you an S multiplying the Mellin transform of G, okay? And so look at this formula and imagine now our unknowns are alpha, gamma, and K0, the fragmentation kernel, okay? You see that you can, at least if you already know alpha and gamma, heuristically, you can divide by the Mellin transform of G in S plus gamma and find an explicit formula for the Mellin transform of K0, okay? At least formally. And it is what we tried to do, what we did indeed. It is to use this explicit formula to say, okay, I take some more assumptions on the fragmentation kernel K0 for technical reasons. So the first line, it's really needed for our theorem. It means that around 0 and 1, you have no direct mass, no creation of zero size particles. And it's continuous in a small neighborhood of 0 and of 1. And the second line, indeed, we don't really need it for our results, but it is needed to have the time asymptotics towards the self-similar profile, okay? That's why we also assume it here. And then under these assumptions, what we proved is that you have uniqueness. Proving existence is a kind of, it's not true. Why? Because if you take any function G, you see these self-similar profiles are solutions of a very specific equations. So proving existence just in abstract, it's not really useful, but we prove first uniqueness. So uniqueness of the whole triplet, gamma, alpha, and K0. And also a reconstruction formula for K0 out of this equation. Okay, so this was with Miguel Escobedo and Magali Tournu. We didn't ask Wei Feng Zhu to sign the paper because it was not totally interesting for his problem. Unfortunately, not yet. So the proof, I will, what time is it? Yes. I will not give you details on the proof, just to tell you it's complex analysis. The first step is to prove existence, to prove uniqueness for alpha and gamma. And how did we do this? We do this using the behavior of the Mellin transform of G for S being very small or very large, S tending to infinity here, for instance. Then we have a behavior of this ratio. It's simply based on the behavior of the Mellin transform of the kernel K for S tending to infinity, because then it tends to 0. And so you have this very specific shape so that alpha gamma, the product alpha gamma is unique. And gamma is also unique because there's a unique R such that this ratio tends to a finite limit. Then once we have gamma, we can also find another way to have alpha. Simply by this explicit formula, we have alpha given by the Mellin transform of G in 1 over gamma Mellin transform of G in 1 plus gamma. So now we have uniqueness for alpha and gamma. And for K0, it will be given by this expansion. So first, we need to prove that this denominator does not vanish. And it's a big part of the problem. So to do this, we use a Cauchy integral, explicit solutions, prove that this explicit solution is also solution of the equation of the beginning. And then we are done. And I also refer to this paper. Vincent is here. They looked at the same question, estimating the fragmentation kernel, but not exactly for this equation, for the gross fragmentation equation, with a specific case of constant fragmentation. Okay, and they also added a statistical treatment of the equation, combining which we didn't do. And so we had existence, and we also have, thanks to this reconstruction formula. But if you look at it, look at this formula, we have only access to noisy measurements of G, of course, in reality. And so this is a severely ill-posed inverse problem because you need to have the inverse mean now. And this is really like deconvolution problem. So in practice, it's extremely difficult to solve numerically. We tried, but it didn't give a really satisfactory results. And moreover, to estimate alpha and gamma, I told you we use the behavior of the Mellin transform of G for S tending to infinity, which means we use the behavior of the self-similar profile G around 0 or around plus infinity, which are exactly the places where you will never have any information. Because what you have are samples of finite sizes. And so you have no information at all. We were a bit disappointed. So we are happy with the math, but not totally happy with the solution, biologically speaking. And look also another problem here. If you see it also very well, this ill-posed character of our problem. Here you have in this inset several fragmentation kernels, okay? And for each color, you have a self-similar profile rescaled, which is drawn here. So you see for kernels where it's high at the boundaries 0 and 1, the blue and the green here, for instance, look at the self-similar profile, how close they are. And you can imagine that when you have experimental data, it's totally impossible to distinguish them, okay? And the same for the kernels who are high at the middle. They are extremely close to each other. It's these three ones. So we get back to Weifeng Zhu and to his data, and we looked at what he did before he met us, okay? So here are the data, and another way to see the data, it's here. So it's the distribution, size distributions over time. So you have here the three different proteins, and you have from left to right, it's the time evolution, I think. Yes, that's it. Another way to see the images, just you draw the distributions, okay? So what did they do before we met? Well, in terms of modeling, it was the same model. It was also the very first reason why we discussed, because he did these assumptions of power laws for fragmentation and of self-similarity for the fragmentation kernel. But of course, he didn't really care of the long-term asymptotics. He simply parameterized his kernel. He solved the direct problem and did some least square to fit the data. And to be honest, it worked. Maybe better than what we did. But it was computationally expensive. And it was not so much informative because it doesn't really give you a flavor of the. So we tried to continue to convince him that we could do something with his data. And we proposed him the following. We said, okay, forgot about the long time asymptotics, but use the time dynamics, okay? Because we have a time dynamics result, which says that it converges with this rate t power 2 over gamma. And let's use it and see if it's possible to obtain the parameters in an easier way, quicker than your least square method. So what we did, we measure the average length of fibrils over time, mu of t here. So f of tx is the u of tx over integral of u of tx dx, which it is what we have access to. It's what I explained at the beginning. And so just work simply a little bit your equation, and you will find that mu of t, normally with our theory, should behave as t power minus 1 over gamma. Here it's just cumulative distribution over time, okay? And so let's try to fit and to find, so in a log scale, it's easier when we reach this behavior like t power minus 1 over gamma, fit the curve and try to estimate gamma with this time-dependent curve, okay? So it is what we did here. the idea is that for the beginning of the experiment, the asymptotic behavior is not yet reached. So we simply take an horizontal line and we estimate, so it is also least square, but only for using very few data in a sense, using only the average size of fibrils over time. And you see, we fit the data with straight lines in the log scale, okay, for the 4 different types of proteins. And you see, it works quite well. It fits the data quite well in the log scale, here in a normal scale. With this, we can estimate not the kernel K0, but at least alpha and gamma. And we have this table, for instance, from which Weifeng is able to draw interesting biological conclusions. I trust him for that, especially saying that alpha-synuclein, which is the only protein responsible for a disease, Parkinson, is less stable than the others, which is interesting in his perspective. And so go back to the data to see if our alpha and gamma are correct. So we choose a K0. Here it is uniform, I think. We depart from the experimental initial condition here, the first line, and then only with alpha and gamma, nothing else, we fit the time dependence curve. And you see, it really worked very well. And at this point, Weifeng was very happy because he, in a sense, it gave him, he understood what was really happening in his equation. He found it beautiful to have only, really it's extremely quick to have these 2 parameters. It's nothing, you see, it's curve fitting. And it really fits well all the time dependent curves, you see, second line. It's really well. And the only problem is that we only used alpha and gamma, and K0 indeed has only a little influence. I will show this here. So here it is with the best K0, however, we can play a little bit around. Here you see if you have a uniform K0, it fits quite well. And now, on the contrary, a delta Dirac, it fits reasonably well also. So the conclusion was that with this type of data, with the self-similar profile, it's not possible to estimate K0, okay, in practice. But even with this time-dependent data, it was not really good either. So then we thought what remains to do? Design new experimental stuff. What could we do? So the first thing we did was some numerical investigation, trying to see when it is possible to distinguish between 2 distributions over time. So here you see tests. You see the p-value of simply a Kolmogorov-Smirnov test, which says, can we distinguish between the 2 distributions? And we departed with 3 different initial conditions. So in blue, you have the spread Gaussian, red, a decreasing exponential, and black, it's a peaked Gaussian. And what we see is that, so here on the left first, you see that when you have, initially we depart with the same condition, okay? And what is happening is that you are able to distinguish between the distributions much better for the black curve when it is a very peaked Gaussian. And it rejoins in a way our intuition, which was, okay, it's not possible with the self-similar profile to estimate K0. What about departing from something totally different and typically a delta Dirac? So this was our idea. So here, okay. So now our idea was not to use the transient behavior, not to use the long time asymptotics, but trying to use the short time behavior of the equation. So let's go back a little bit of the theory. So here I just put our usual assumptions on K0. And I write what is a weak solution, because if we want to depart from a delta Dirac, we need to define measure solutions of the equations. So I write the equations on a weak sense. So I take a test function phi, and I simply rewrite, maybe it's more familiar, by the way, to you, the equation written under this form. And we can have existence and uniqueness in several papers, several works, I think. At least for gamma strictly positive, because when gamma is negative, I told you it's different game. And so heuristically first, let's try to see what happens at short times, okay? So take the equation and look. So du over dt, I write a small asymptotic development. I say it's u of t plus delta t x minus u of t x over delta t, okay? The fragmentation here, alpha x power gamma, I take it in u of tx as for an explicit scheme. And now on the right-hand side, the same, I take u of t instead of u of t plus delta t, okay? And now I do this between delta t small and time 0. And at time 0, I choose for an initial condition a delta Dirac in 1. So since it is in 1, the x power gamma here turns to be 1. Okay, there is a small abuse of notation here, but I'm sure you will excuse me. And so at the left-hand side, at the right-hand side, what do you find? A small miracle, you find exactly your fragmentation kernel. It appears that the fragmentation equation, and it's totally logic if you think of it, but it took us a lot of time to think it. It's logic. The idea is to have a short time, so you can neglect the particles which have divided twice. And if you depart from a Dirac in 1, you have, of course, many particles which have not divided, but the ones who have divided only once, they simply are along the fragmentation kernel K0. And that's it. So the idea under that is really simple. And so having this formula, we can say, okay, nice. We will take K0 of x as 1 over alpha delta t times u of delta t x minus 1 minus. So these are the particles which have not divided, 1 minus alpha delta t times the delta Dirac in 1. And that's all. This is heuristic. Now let's look a little bit at the numerical simulations. It's really very beautiful, I think. So here I have drawn a u minus the delta Dirac in 1 times exponential minus alpha t, which are the particles which have not yet divided. Okay, since I take alpha equal gamma equal 1 here for 4 different kernels. I haven't drawn what are the fragmentation kernel, but you can guess what they are because you will see it. So at initial time, the smallest time, at initial time you have a Dirac in 1, but the smallest time it's in blue. I hope you see it in blue. So here you look, the blue it's here. So what is the kernel? It's of course the uniform kernel. Okay. Here you see the kernel, you really see the kernel exactly on the blue curve. Here it's a strange kernel with 2 peaks, and here it is this one. And then if you continue, time becomes bigger. The last time for the simulation here, it's the red one. And what do you see here? The red one, it's exactly the exponential that you expect, which is the self-similar profile for the uniform kernel. And here at each time you see in red the self-similar profile. So in a sense, the fragmentation equation when it departs from a delta Dirac, transforms the kernel K0 into the self-similar profile. You see? And so now let's do this a little bit less heuristically. We have a first result in the total variation norm, which tells you that indeed, if you depart from the solution from delta Dirac at time 0, then you have this asymptotic result, u of t, asymptotic for small time. U of t minus what I expect, exponential minus alpha t delta Dirac in x equal 1 over alpha t minus the fragmentation kernel k0 in total variation norm is smaller than k times t. So it tends to 0 and t tends to 0. However, this result cannot be used, just look at the time, cannot be used directly by biologists. Why? We asked Wei-Feng, we told him, what about the departing of delta Dirac? And he said, no, I cannot. Why not? Because experimentally, you never have exactly a delta Dirac. But he can have, I think he cannot, but maybe other people could, or maybe later he will be able to. We could depart from a Gaussian peaked at some point, at least. And so we need a result with some noise and not only this perfect result. And so the two difficulties are first, difficulty to have a delta Dirac at time 0. And second, we will never measure exactly the initial condition, but always with noise. So we need a result which would include noise and also the fact that we depart from not exactly the delta Dirac. So it is what we did here. So we assume that we depart from the real initial condition uq0, which is such that its distance to the delta Dirac in 1 is small. Q is expected to be small, okay? And we also expect that we have measurements, experimental measurements, which are noisy. So here I did it in this norm, bounded Lipschitz norm. It's a pity that but you don't see the definition to the end, but you guess it, huh? Okay? And in bounded Lipschitz norm, we also expect that the measurements uq0 epsilon 0, yes, it's better, thank you. And uq epsilon in time, so we have two measurements at time 0 and measurements at time t. Another difficulty experimentally also is that to have a very small time. It's not so clear. And then with these assumptions, we have an estimate no more in total variation because it would be not interesting in our case, since we depart, for instance, for Gaussian and the delta Dirac, it will be far away in total variation norm, but not in this bounded Lipschitz norm. And so you have this estimate. So now exactly the same formula on the left-hand side, you see, as you had here. It is smaller than, and you see the typical shape of a balance between time large and time small. You have first a constant k times t, as you had here. But then you have the noise terms. The noise terms, you have something small at the numerator, k2q plus epsilon 0 plus epsilon, divided by alpha times t. So that when times is too small, this term will explode. And so you have a trade-off. You need to choose time small enough to have, but not too small either. Okay. And do I have time to give you a flavor of the proof? Yes. Yes. I don't know if. So first, why did we choose the bounded Lipschitz norm? First of all, to have something which is well adapted to measures. Also because, so when you have two delta Diracs close, so it's a norm which is, I refer to this paper by Benedetto Piccoli, Francesco Rossi, and Magali Tournu. It's still a preprint, where they explained how it is a kind of, you can also see it as an interpolation between the total variation norm and the Wasserstein norm. So that you can extend the Wasserstein norm to signed measures having not necessarily the same weight. Typically, this is the ideas, and also it is smaller than the norm in the total variation sets. So it's very practical. Okay. So how do we do the proof? I will try not to make you sleep too much, but you do a series representation of the solution, time series, and you prove that the series converges for all time between 0 and big T. And then simply, and it comes, and the first coefficients, A1 happens to be exactly K0, okay? And this representation exactly corresponds to splitting into particles having divided once, twice, etc. A number n of times. And this gives you the first result, the total variation result, okay? For the bounded Lipschitz result, yes, and having this total variation result, another thing which is interesting is, of course, if you depart at a delta Dirac in a given lambda and not in one, you simply use your rescaling and you have another result, which tells you that you just have to multiply here exponential minus alpha t by lambda power gamma, divide by lambda power gamma. Here you have a dilation of K0, and you have a lambda power gamma on the right-hand side, okay? And what is nice here is that then you can also depart from other types of initial conditions. For instance, due to the superimposition principle, you can depart from NA, and then what do you find? You don't find exactly, sorry, there is a typo, it's not kappa, it's K0 here. You don't find, you don't go to K0, but you go to K0 and we convolved with the initial condition, denoted here mu0 and not u0, two typos, I'm sorry. Vincent, you see, sorry. And what else? For the bounded Lipschitz norm, it's not, you simply use a triangular inequality to estimate. Many terms are already included into the assumptions. And so we want to estimate this term. So you have, and there remains only one term to estimate. So either it's directly the assumptions, these three terms that you find here when you do a triangular inequality. You have one term which is estimated by the total variation theorem, thanks to the fact that the bounded Lipschitz norm is smaller. Okay. And finally, you have this term uq minus big U of t, which simply, for which you simply need a kind of stability result for the solution, time-dependent solution. So it's this proposition here. If you depart with a U0, a given measure compactly supported, then between 0 and big T, you have you can bound the solution U of t by the initial condition U0. Okay. So well, the theoretical work is more or less finished, but we have not yet applied all this to true experimental data. To conclude, I would say that in our case, asymptotic theory is mathematically interesting, but not very helpful in practice. However, we can obtain good estimates of alpha and gamma with this time-dependent solution. And the short time, I think, is really promising and interesting, and maybe could also be studied with stochastic processes. And there is Guillaume Garnier who will do his PhD on subjects close to that. And also, maybe some of you is interested in that. Okay. And I had finished, I have still the 2 minutes for the small video, which I will not explain to you in detail, but which was inspired by a paper by Jean. Ah, it doesn't work, okay. So just me. Yes, you see it? So, okay, it's a fragmentation equation, but in the case of constant fragmentation, Jean has proved that there is a central limit theorem of a kind. It converges to with a certain rescaling to a Gaussian, etc. But here, with the diagonal kernel, you see there are all these oscillations, which are not contradictory with the weak result of convergence toward a Gaussian. but you see it's a beautiful, it's only deterministic, but I find it beautiful to, for me, it was not obvious to find a Gaussian, and I found the explanation with probability. So thank you very much. And,
thank you very much, Marie. And are there questions? Yeah.
Hi. Is it only for the sake of biological plausibility that the fissions are binary, or could you take a more general kernel?
No, indeed, we don't really need a binary. In all this talk, I don't really need binary. Everything is okay without, moreover, I think I try to expand it. Comment on fait? Attends. Sorry. I tried to, no, I doesn't, yes. Okay. I think in our results, we didn't use the fact that it's binary. We only use the fact that there is a finite number of fragments. And that's all.
Okay. Maybe I have a second question. So for the fragmentation rate, so you take a power law, and you mentioned something like only the behavior around 0 is important. So
you mean there is no
like
more
for B of X?
For K0?
I think for B.
For B of X?
Yes.
Yes. So indeed, there is, for gross fragmentation equation, it's something we have much studied. For the, maybe if I look here, I've written the equation with x power nu for the gross and x power gamma for the fragmentation. And in such a case, you have an interplay between nu and gamma, both around 0 and around infinity. But since we have taken so simple cases, it's the same condition around 0 and around infinity. It is typically that you need a link between 1 plus gamma minus nu. If they are strictly positive, then you have this nice self-similar profile or Malthusian behavior. If it is equal to 0, it is the limit case that, for instance, there are recent papers by Miguel Escobedo, who has studied it, and also Jean Bertoin and Alex Watson have studied it. And gamma negative, for me, there is not much. There is mainly this paper by Benedict. Benedict maybe knows if there are more, or Jean, you know. It's really a tricky case. You have a... do I answer the question? I'm not sure, certain. You had...
So what I wanted to know is really if only the behavior at 0 and infinity was important, so you could take whatever function.
No, both are important.
Yeah, okay.
The reason is that around 0 it's important because you don't want to create dusts, for instance, but in infinity it's important because you don't want cells or particles grow at infinity.
Yeah.
You see?
Mm-hmm. Thank you.
Thank you, Mary. So you focused on the pure fragmentation case, but since you are considering small time, couldn't you, I mean, would your method also apply for gross fragmentation equations? I guess it's because in a small time, particles do not have time to grow much.
To grow much?
Yeah.
Oh, yes, I think it should. Yes.
Okay.
Yes, it should. I don't have any experiment in mind, but we tried to see that with Weifeng, and he said he will try to add growth in his experiments because we tried to explain him that when you have growth, strangely, it simplifies because it can give rise to a steady distribution, much easier to measure, etc. Yes, the problem is these small time measurements. I don't know if it's really easy to measure these small times measurements.
I had a second question about it, because if your time measurement is too small and you have only too small number of fibri, you won't see anything.
Exactly.
So what is the trade-off between?
Yes, that's exactly the problem. I think it's given by the it's given by the result at the end with the bounded Lipschitz norm. Typically, we expect time in the square root as in the square root of the noise. Roughly speaking, to have kt plus noise over t. But what does it mean exactly? We didn't try. Yeah. We don't have experimental data. First, we'll try on simulated data, and this is not done yet either. So.
Any other question?
Yes, so you assumed since the beginning that you are in a self-similar situation with Bx to the power gamma. Do you know if the biologist or statistician have some methods or some hypothesis tests to see if their data fits indeed this assumption that we are in a self-similar model?
This is really interesting. I think I'm not aware of them, of such methods. I know for bacteria, we have tried to estimate. There is also another paper by Nathalie Krell and co-authors, I think, not Vincent, I think this time, where they have done it. No, it was for the growth rate, I guess. When I plotted it, I see clearly that it was not correct, meaning that very large cells, bacteria, tend to divide into unequal daughter cells. So the idea is generally to do this assumption, and then afterwards we test whether